Hey there, Stat Nation, Statman here. This is chapter 5, day 13. It is actually the last day before the test. So let's get started. All right, question 1. These are all kind of practice questions. Question 1 comes out of a table. You can read the prompt yourself. It's got to do with 52 athletes, and it's got to do with swimmers. So question A asks, given that the individual is a female, so there are 26 females, what's the probability she's a swimmer? So that would be 6 out of 26 right there. Okay. Next question. B, given that the individual picked is a swimmer, that's 16 of those, find the probability that he is a male. So that's 10/16 right there. Those are all considered conditional probability because you're not using the table total of 52. You're using the conditions that they give. Okay. I really like question 2. Question 2 is about vaccinations. Kind of a cool question because we've dealt with it so often, so recently. Are vaccinations worth it? Do they work? This is actual data. I forget where I got it, but it's a small community. And it asks some pretty simple questions. So here's vaccinated, got the flu, didn't get the flu. Take a second to familiarize yourself with this. Not vaccinated, and they can still get the flu or not get the flu. Let's make heads or tails of this, okay? I got all of I'll underline them, all of the conditional totals, and then I'll put a box around the table total. All right. So, question A, if a person was vaccinated and got the flu, okay, what's the chances they were vaccinated and got the flu? That's 60 of the 400, okay? Question B, the person got the flu given they were vaccinated. So, got the flu given they were vaccinated. So, vaccinated is 250 people, and then got the flu is here. Okay, so there's that one. Okay, question C, the person didn't get the flu given they weren't vaccinated. Okay, didn't get the flu given that they weren't vaccinated. All right, so let's see here. How many weren't vaccinated? 150, and then didn't get the flu, that would be 65 of those. And that if you make that into a decimal, it's about 43%. Okay. And then item D right here, the person was vaccinated given that the person got the flu. So given they got the flu, that's 145 people. And by the way, the given, if you haven't figured it out, is the denominator. The numerator is the first part. The person was vaccinated, so that's right here. Okay. And then you can make that into a decimal. I really like question E and F. They are really cool. Are the flu and vaccinations independent? Now, when we get to the chi-square distribution later on in the book, you're going to be able to answer this question a little more fully. But right now, you're going to examine one of the 2 cells, and one of the 4 cells. We've done this in class quite a bit, okay? So let's take the probability of getting the flu. Getting the flu right here is 145 out of 400. See that? 145 out of a 400, okay? And then being vaccinated is 250 out of 400, okay? So if you take those fractions and multiply them together, you get 0.2265. So this number I'll box it, that's boxed, represents the probability of getting the flu while being vaccinated, what it should be if the events are independent. But we have the truth of it. The truth is that 60 of the 400, I'll circle that and put arrows next to it. The truth is 60 of the 400 were actually had the flu, even though they were vaccinated. It was only 15%. So if they were independent, you would run 22.65% of people that were vaccinated would still get the flu, but it's only 15%. You can see how much the vaccination helped because it drove it down. If those numbers are relatively close, you could say they are more or less independent, but they're not close. That is a major reduction. It's about a, I don't know, it's about a 33% reduction, something like that. And that is definitely an indicator of not independence, that there's an influence. And you better hope that vaccinations and the flu are not independent, because then why get them? They've got to, force something to happen. That's a really cool prompt. You've got to be able to handle this kind of problem off the table. Okay. Now, which of the following is true? Flu and vaccinations are, well, they're dependent. We proved that they're not independent, and not independent means dependent. Okay. But they can happen at the same time. And that means not mutually exclusive. They can happen at the same time. Okay. So, and by the way, note on item F here, one of these is actually not possible. Should take a second and figure this out. So the one that's not possible is, let's see here, I think is A. Yeah, is A. If things are independent, okay, if you are mutually exclusive, if you can't happen at the same time, then you are actually dependent. Think about that. Item A is impossible. If you are mutually exclusive and you can't happen at the same time, as soon as one happens, the other one cannot. And that means they are actually somewhat dependent on each other. Okay, so keep in mind that A is actually impossible. And that could be a question they ask too. Which one's impossible? Okay, let's go down to number 3. 2 employees on a college campus, Brian from operations and Beth from safety, are assigned to check that a certain building on campus is locked over the weekend. Suppose that on any weekend, the probability that Brian checks the building is 96% and Beth checks the building is 98%. Okay, so they're checking it and they both check as 95. What is the probability that neither Brian nor Beth check it? Okay, so the first thing you may want to notice is these are not quite independent, because 0.96 times 0.98 doesn't equal the given of 95%. It's awfully close. So they're close to independent. This, if that happens, then you should be doing a Venn diagram. And I'm going to do the Venn diagram right here. I'm going to do the circles. Here's the circle for that one. Here's the circle for that one. Always start where it says both. Both is the key word. Put 95 there. The reason 0.01 is here is this 0.01 represents the probability of only Brian checking, doing that safety check. Okay. And this 0.03 represents where only Beth checks. Now 0.01 and 0.95 make 96. So that's how I got that. And 0.95 and 0.03 make 98. So we're good on that. Okay. Probability that neither. Okay. So if you add these up, 95 and 3 makes 98, plus 1 is 99. And then you go 100 minus, it's only a 1% chance that neither checks it. Okay, that's a Venn diagram problem all the way. Okay, now number 4 is kind of cool. It's a little bit different. A petroleum company is exploring for oil, has decided to drill 2 wells, one after another. The probability of striking oil in the first well is 20%, given that the first attempt is successful. The probability of striking oil in the second is 80%. What is the probability of striking oil in both wells? Now, this is a really easy question. You really don't need the tree diagram, okay? If you did the tree, you have 0.2, and then event B is 80 and 20, correct? Now, event A, if there's no oil in the first one, we're not going to keep going. That's why this is blank. But really, you're just doing 0.2 times 0.8. That's not really that hard. It's 0.16. You could use a tree diagram. You may choose not to because it's fairly easy. Okay? All right, number 5. Okay, number 5, a person, let's see here. A person owns 5 stocks. The probabilities are exactly 1, 0, 1, 2, 3, 4, 5 that of the stocks goes up in price in a given day are respectively blah, blah, blah. Fine. Okay. So you could make a table of this, but it's pretty easy to manage this. All right. So read that problem. At least one stock goes up. Well, the probability that none go up on a given day is 0.1. So you can just go 1 minus 0.1 and get 0.9, or you could add these up. I could box all these. It's a little longer, but you get the same answer. Okay. The second one is at most 4 stocks go up. At most 4. That means, let's see here. At most 4, that is going to be 4 or fewer, correct? So you're going to add up basically these right here. You're going to add up all these, okay? Or you're going to go 1 minus 0.08. Either one's fine, okay? So hopefully that's pretty easy for you too. All right, number 6. Number 6. We got television channels 7 and 10 are affiliated with the same network. The probability that channel 7 carries a particular sports event is 50%. That channel 10 carries it is 70. And probably they both carry. There it is, both. We got a Venn diagram. What is the probability that you can watch either probably on either channel? This was like the Super Bowl in the early years. 2 networks were carrying it. All right. Anyhow, there we go. There's that. There's your Venn diagram. Always start where the both is. So channel 7 is 50% total, which you can see added up here. Channel 10 is 70% total. Okay. And it asks, what's probably you can watch the program on either of the channels? There's actually a 90% chance here. Okay. Because you're going to add 0.2, 0.3, and 0.4, or you can add 0.5 plus 0.7 minus 0.3. That's going to give you the same answer. There's 2 ways to do that, okay? We have definitely studied that quite a bit. Okay. Number 7, this is our last one. This is a little trickier. This is a Venn diagram problem. We haven't done this a whole lot. A town has 2 ambulance services, okay? In an emergency, the probability that the city responds is 60%. Probability that the private service responds is 80. And the probability that either of the services responds is 90. Ooh, so this is a little unique. Let me draw this out for you. This would be one we probably haven't seen. So we do not know, if you read closely, we do not know the probability of both, okay? But we know, I'm going to label both responding as X. We don't know what it is, okay? They want both, but we don't know what it is, okay? So the city total is 0.6, okay? So this part of it will be 0.6 minus X, okay? The private is 0.8. So this will be 0.8 minus X. And we know that if we add all 3 of them, let me change colors here. If we add all 3 of them, this one, and this one, that's going to equal 0.9. I'm going to box the equation. It's going to equal that. But then you just got to solve for X using algebra, and it comes out 50%. Now, if you want to double check that to see if it works, put 0.5 in there. That makes this 0.1 for a total of 0.6. That makes this for 0.3 for a total of 0.8. A really cool question would be, find the probability that neither respond. That would be this one out here, 0.1. Okay, so there are those 7 problems. Okay. That is it for chapter 5, day 13. Good luck, Stat Nation. Take care.